Hello, everybody. My name is Tage. I'm a PhD student at MIT.
I'm Ralph, and I'm a postdoc also. I'm a postdoc at MPI SWS.
I'm Joe, and I'm an assistant professor at Boston College, and you're in the right place for the Iris tutorial.
So if you haven't seen all of our messages, you can clone the tutorial lecture material from this URL. That has both the slides that we're presenting from here, as well as some exercises, which we'll get to at the end. You can follow the README to install Iris and follow along on your own. We're aiming for the lecture material to take about an hour, including a bit of a Coq demo. And then we want to give you some time to play around with Iris yourself. We also have a Mattermost channel where you can get help along with the other participants. And we'll also be around through the rest of POPL if you have more questions and you're working on the exercises. Okay, so what is Iris? So Iris is described by this long phrase, language independent. It's a language independent higher order separation logic with simple foundations for verifying fine-grained concurrent programs in Coq. So what does that actually mean? Let's break that down. So first of all, Iris is based on a higher order separation logic. Higher orderness here helps support modular reasoning. And it also supports reasoning about higher order stateful programs. So these are programs that have mutable memory and can have first-class functions that are passed around. Iris is applicable to fine-grained concurrent programs. It can reason about low-level synchronization primitives like the implementation of things like locks and channels, all the way up to coarse-grained concurrency of programs that are using locks. Iris is language independent, so the foundations are just a core logic that doesn't know anything about programs or a language. And then the higher level infrastructure is parameterized by the language. Iris ships with a simple language called heaplang, which is used for many of our examples, but it has been instantiated and used for versions of more realistic languages like Go and Scala and Rust. And finally, Iris is based on simple foundations. Relatively simple foundations. It has a small canonical set of primitive rules. And the main benefit that this provides is twofold. So there's a benefit to the Iris implementation itself in that the implementation is more modular. We can separate out all the language reasoning from the core logic. And this also benefits you as a user because it means that the library is well engineered to have good, clean abstractions that you can build on top of. And finally, Iris is a Coq library that supports all of the above. So the fact that it's a Coq library means that we have machine check proofs, both for the Iris implementation, as well as for a number of projects that are built on top of Iris. And as we'll see, when you actually use Iris interactively, what we mean by it provides practical support is that Iris is actually quite productive to do verification inside. It allows you to do verification at a high level of abstraction where Coq is actually assisting you. Iris is very versatile. It's been used to formalize many projects with a range of results from program logics to logical relations to sort of more bread and butter program proofs. Now, the authors of this tutorial, we've mainly worked on two large projects, Rust Belt and Perennial. So we'll describe those in a little bit of detail, but then we'll hint at some other recent examples that use Iris, which we didn't work on directly.
Right, so before I explain Rustbelt, I have to say a few words about Rust. Rust is a young but strongly growing systems programming language, which aims to break the fundamental trade-off between low-level control, as we know it from languages like C and C++, and high-level safety guarantees, as we know it from pretty much any other language, and aims to provide both in a single language. And the way it does that is through a sophisticated type system, which doesn't just describe the shape of data, but also exclusive ownership and how ownership can travel between functions and threads. And it comes with a notion of temporarily borrowing that ownership to some other party for a certain lifetime. However, even without all that sophistication, the Rust compiler isn't smart enough to verify the correctness of all of the crazy low-level things people might want to do. So one important aspect of the Rust ecosystem is to be able to write unsafe code that you have to be careful about and check yourself manually, which you can then wrap in a safe abstraction so that all of the users of this code, which will be obviously many more than just the implementation, are protected from misuse of that API. So the goal with the Rustbelt project is to verify that this encapsulation is actually done correctly. And to this end, we've built what is called a logical relation. So this is using Iris not for program verification, but to give meaning to the types of a type system in the sense of the kind of invariants that a certain type expresses about its data. One key ingredient here is what we call the lifetime logic, which extends separation logic with the notion of borrowing. And this is really where we've put the ability of Iris to define new abstractions and to verify them ourselves inside the logic to the limit. With all of this, we've been able to verify, for example, the mutex type in the Rust library, which provides safe concurrent access to shared mutable data to Rust code.
So Perennial is another project that was built using Iris. The problem that Perennial is trying to solve is to prove the correctness of storage systems. And for this, think of file systems or maybe a key value store that's manipulating on disk, that stores its data on disk. Storage systems need proofs of correctness both under failures, such as if the kernel panics or if you disconnect the disk, as well as under normal execution. And what we did in Perennial is we used Iris to build a variant of for logic that has not just a post condition, but also a crash condition, which holds at all intermediate points while executing a function of interest, even on failure. So this variant of for logic, which we developed, gives the Perennial logic the flexibility to combine concurrency and failure reasoning. So we use Iris for the concurrency aspects, and we extended the logic with failure reasoning. And Perennial is was an example of a project that does use a custom language in order to reason about executable code written in Go. There are many other projects using Iris. This is just a small sampling of recent examples from the last couple of years. The first one, concurrent search templates, uses Iris to prove some data structures correct. So this is an example of just using Iris to prove some programs. Anaris is also a new program logic like Perennial that's intended for reasoning about distributed systems. Scala step-by-step and Hazel, Scala step-by-step is a little bit unusual in this list because it formalizes the Scala type system, and it doesn't actually use Iris for any concurrency reasoning. It just uses Iris to handle step indexing. So this is a slightly unusual and cool application of Iris. And finally, Hazel doesn't have any concurrency. It's a sequential separation logic that has support for effect handlers. And it uses Iris in particular to handle defining recursive predicates. And Hazel is actually going to be presented at POPL. It's the first session on Friday. Okay, so the outline for the rest of this talk is, so we've kind of given some motivation by talking about how Iris has been used. And what we'll do next is we'll go into some of the actual details of the Iris logic. The first part, we'll talk about invariants and Go state. So this is kind of more background. Then Joe will talk about that. And then Ralph will go into how we actually model Go state using PCMs. This is the general infrastructure that Iris provides. And then finally, we'll do a live Coq demo just to get you a feel for what it is like to use the Iris implementation. And then we'll let you go to work on the exercises, and we'll be around to help out with those.
Okay, so now that we've seen some applications of Iris, let's get into the details of how we use it to reason about programs. So you may have seen Hoare logic before, and recall that in a Hoare triple, there are three parts: the precondition, here P, a program expression, E, and then a postcondition, Q, where in Iris, we write the postcondition with an extra bound variable here, W, which is going to represent the value returned by E's execution. So the meaning of such a Hoare triple is that if we show this holds, and then if we execute E in a state satisfying P, then we're guaranteed two things. First, E is safe to execute, meaning that E won't get stuck or crash or trigger undefined behavior. And second, if E terminates with some return value V, then the final state after E executes will satisfy the post condition with that return value V substituted in for that variable W. So separation logic adds sort of two core key ideas on top of basic Hoare logic. The first is this new assertion, the points to connective, which we write as X, and then this maps to arrow, and then a value V. So the way to read this is it's X is some memory location or memory address, and V is a value. And what this is saying is that that memory location X stores the value V, but also when this assertion occurs in a pre or post condition, we read it as not just asserting that description of the state, but also kind of representing exclusive ownership of X. That is, the right to access and modify that location in memory. And then the separating conjunction is the other big idea. It's a new assertion written P and then this asterisk or star Q. And the meaning of this is it holds in some state if it's possible to split the state up into two disjoint pieces, one of which satisfies P and the other of which satisfies Q. So if we take a look at a Hoare triple for a program swap, which is going to take two pointers X and Y as input and commute their contents, then a specification like the following for that. In the precondition, we have that X points to V1 star, Y points to V2. So that's telling us that X and Y must be different locations in memory. Why? Because the fact that there's a separating conjunction there means we need to be able to split up the program state into two pieces, one of which contains the X address and the other which contains Y. Therefore, X and Y can't be the same. And moreover, this is telling us that the execution of swap has the right to read from and modify those program addresses, which makes sense because it's going to need to commute their contents. And then the postcondition tells us that indeed they've been swapped, and again, they're still separating conjunction. So O'Hearn's insight is that this reading of the separating conjunction and the points to fact as letting you partition state up into pieces that are exclusively owned lends itself to reasoning about concurrent executions in a thread modular way. That is, we're able to verify individual threads and then compose them together to verify concurrent execution. And that's captured by the following PAR rule of concurrent separation logic, where we write E1 and two vertical bars, E2, to mean the concurrent execution of two threads, one running E1 and the other running E2. So what this rule says is if we have a precondition that we show can be split up into disjoint pieces, P1 and P2, via that separating conjunction. And as assumptions, we've proven triples about E1 and E2, showing that E1 requires P1 as a precondition and E2 requires P2 as a satisfactory precondition. Then it's safe to concurrently execute E1 and E2 together. And in the postcondition, what we get is the separating conjunction of the postconditions of each of those triples we proved. So the intuition behind why this rule is sound is that, well, our assumptions tell us that E1 only needs access to the parts of state described by P1, and E2 only needs access to the things described by P2. So if in the precondition we're able to split those up, show that P1 and P2 are in disjoint pieces of memory, then that's telling us that these two threads aren't going to interfere or interact, so it's safe to run them concurrently. So for example, if we consider this program where we have two threads concurrently executing, one of which reads from X and writes back the value with 2 added on, and the other doing the same thing but for Y. Here in the precondition, we're going to assume we have the separating conjunction of X and Y. And so what we do when we invoke the PAR rule is we can imagine passing ownership of the X points to 4 fact to the thread on the left, and the Y points to 6 fact to the thread on the right. And then each of those threads now, that's a satisfactory precondition for what they need, because X needs to be able to read from and write to, or sorry, the thread on the left needs to be able to read it from and write to X, and the thread on the right needs to be able to read from and write to Y. Okay, and then afterwards, we join back their post conditions at the end to conclude that X points to 6 and Y points to 8. So this works quite well for reasoning about concurrent programs where threads do not need to share memory or interact. So for example, if you think about a concurrent implementation of quicksort, where after the partitioning step, we launch threads to handle recursive calls, and each thread operates on a distinct sublist of the original list we're trying to sort, then the PAR rule works well for reasoning about that because they have disjoint memory accesses. Of course, there are many concurrent programs where we do want to have shared memory accesses. For example, let's consider the following program where we allocate a memory address X, and then we have two threads that concurrently execute, which each atomically add 2 to X using this atomic fetch and add operation. So if we think about trying to verify this with what we've seen so far, well, we would like to prove that after this, these two threads join up and we read the value of x, the return value should be 4. So after we allocate the reference for x, we get the points to fact saying that it contains 0. But now we're stuck because the left thread certainly needs to read from and write to x, but so does the thread on the right. However, the x points to 0 fact is asserting exclusive ownership, and there's no way for us to split that up and give it to both the left thread and the right thread. So we can't invoke the par rule with what we've seen to reason about this program. The solution for reasoning about shared memory accesses in Iris is to use what's called an invariant assertion. So an invariant assertion has the form box, and then you put inside of that box some other assertion R. And what this is saying is that R is an invariant of program execution, meaning that once established, it holds before and after every step of execution. So we work with invariants through a couple of rules. First, we have the invariant opening rule, which tells us that if we have in our precondition that R is an invariant, then we can open up that invariant, get access to R in the sense that we add R unenclosed by this box to our precondition. But what we're required to do is show that R still holds in the postcondition. That is, we reestablish the invariant. And moreover, we require that E, the expression we're reasoning about, be atomic in the sense that it reduces to a value in a single step of execution. So this is really capturing and forcing us to ensure that the invariant, we get to assume it holds before our step of E, but then we have to show it still holds afterwards. Okay, and that's necessary because another thread might want to rely on this invariant and open it, so we need to maintain it. We can create an invariant if we have R in our precondition, then a thread, we can choose to give up exclusive access to R by creating an invariant and storing R inside of the invariant. And now other threads can access it using this invariant opening rule. And then finally, the important fact is that invariants are duplicable in the sense that box R implies box R star box R. So what's nice about this is that having created that invariant, we can now make multiple copies of it and pass them to each thread that needs it in the par rule. Okay, so there are two technicalities that we're going to omit in this talk, but which do arise in the Coq implementation. The first is that we need to actually annotate invariants with names and also annotate Hoare triples with the names of invariants that are able to be opened. This is just a kind of bookkeeping to make sure that we don't try to open the same invariant twice. The second technicality is that in the opening rule, when we open up the invariant, we don't actually just get direct access to R, but we get R guarded by the so-called later modality triangle that comes from step indexing. And this is a technicality that's needed to support nesting of invariants, like if we wanted to put invariant assertion inside of another invariant. However, there's a theorem in Iris that says that for a large category of assertions R that don't involve this kind of nesting of invariants, you can ignore this later modality and get a version that doesn't have the later occurring. So for our purposes here, we're just going to ignore both of these technicalities. Okay, so now that we've seen the rules for working with these things, let's take a look at how it can help us to solve the issues we saw in reasoning about this fetch and add example from before. However, as a first cut, what we're going to do is not prove the full spec showing that at the end we get a return value 4. For now, we're just going to show that the return value is even. Okay, so as before, after we allocate the reference cell, we get the points to fact saying that x points to 0. And now what we're going to do is we're going to put that points to fact inside of an invariant so that we can share access to it across multiple threads. So in particular, the invariant we're going to allocate is going to say that there's some number n, which x points to, and n is even. Okay, and now using the duplicability of invariants and the par rule, when we fork these two threads, we can pass in a copy of this invariant assertion to both of them. So now let's take a look at what the thread on the left is going to do. It's going to open up the invariant it got using the invariant open rule, which is going to give it access to some x points to n for some n, and knowledge that n is even. And then the result of fetch and add is going to add 2 to n. So now x will say n, and now we'll have that x points to n plus 2. And of course, since n is even, n plus 2 is also even. Okay, so after fetch and add has finished, we've reestablished the invariant. And so we're able to properly close the invariant as that invariant opening rule required. And of course, the thread on the right is going to do the same thing. It's the same piece of code. So now at the join point, when the two threads finish, the parent thread has this invariant. In order to read the value of x, it's going to open up the invariant, get out that x points to some n, and that n is even. The read from x preserves the invariant since we're not modifying x at all. And we get to hang on to the knowledge of this pure first order fact that n is even. So we're able to deduce at the end that in fact the value we returned was even. Okay, so now, of course, let's see, we'd like to actually prove the stronger spec of showing that the return value is not merely even, but was in fact equal to 4. And for that, we're going to need another ingredient of Iris, which Ralph is going to describe.
Okay, so hold on a second while I take over. Okay, you should now be able to see my screen. Okay, so yes, so what we're trying to fix about the first proof is the problem that we were only able to prove that the result is even and not the exact value. And fundamentally, the reason why the first proof isn't good enough for this is an issue of information loss. So if we look again at this invariant that we declared, then what we have as an invariant is just there exists some n such that x points to n, and we also knew that n is even, but we entirely forgot the value of n. It could be 0, it could be 200. There was no way for us to remember this. We have to find some way to abstract over the n in the invariant without entirely forgetting what the current value of n is. And so the way we're going to do that is with a kind of ghost variables that are supported by Iris. And what's special about these ghost variables is that they come in entangled pairs. So we have two new kinds of assertions here in the logic, which look a bit like the points to assertions that we've already seen, but they don't say anything about the physical heap. These are purely logical. So we write them with a different kind of arrow, with this hooked arrow. And they come in two different, they come in pairs, which have two sides. On the one side, we have the authoritative version of this ghost variable ownership, which we will typically put into the invariant. And on the other side, we have a fragment version. We write that with an open circle. And that is what we will keep around in the Hoare triple. And the magic now is that these two are entangled in a sense, so that they will always point to the same value. And that way we can abstract over the current value in the invariant without entirely losing track of it, because we have this entanglement kind of back channel. Of course, to do anything with these ghost variables, we don't just need a way to express them. We also need some proof rules, some reasoning principles. So the first proof we're going to look at is the allocation rule. And this one uses another new funny connective, which is this 3-line arrow with a big asterisk on the right, which is, we call this a view shift. And you can think of it like a Hoare triple without any code, because the effect of a view shift is that it changes the ghost state, it changes the logic it states. So it's in a sense imperative, like executing code is, but there's no actual code, because the only thing it changes is purely logical Iris state. The physical heap of the program is unaffected. That's why we can emit the code, and we can treat it a bit like an implication. And indeed, when we're doing verification in the context of a Hoare triple, we can essentially think of this as being implication or magic wand, if you want to be more precise. So the allocation rule now says that at any time with the precondition of true, we can allocate a new ghost variable. It will get some fresh name gamma, which correlates the two entangled parts, and then we own both of these parts. The two other key proof rules that we obtain is, first of all, we get this entanglement property. So if we own both parts, we learn that the value n of the authoritative part with the closed circle and the value m of the fragment part with the open circle are in fact equal. And secondly, we get a rule that lets us change the current value. After all, this is supposed to be ghost state, so it's mutable. And indeed, so what this shows is if we own both of them, we can change it to a new value n prime. But of course, it has to be the same new value n prime for the authoritative and the fragment part, because we have to preserve this entanglement. So now let us see how we can use this new primitive of a ghost variable to perform the proof and get the desired specification. The beginning of the proof is the same as before. So we allocate x and we obtain ownership of x points to 0. But now before we allocate the invariant, we will allocate two of these ghost variables, which will track the contribution of those two threads to the overall value of x. So we have gamma 1, which tracks how much the left thread has already added to x, and gamma 2, which tracks how much the right thread has already added to x. And of course, initially, both of this is 0, and we own the authoritative and the fragment part for both of them. And now we allocate the invariant, which now, of course, contains ownership of x as before, but also contains ownership of the authoritative parts of both of these ghost variables. And it says that the value of x exactly equals the sum of the values of these two ghost variables. Ownership of the fragments for both of these ghost variables is retained in the main thread. We didn't put it into the invariant, so we still have that around. So we now have this back channel where the invariant doesn't know what n1 and n2 are, but we actually still know that both of them are 0. Now we can use the par rule again, doing parallel composition and giving ownership of the gamma 1 fragment to the left thread and the gamma 2 fragment to the right thread. And as you will see in a minute, we are able to prove that the effect of the fetch and add is that the value of those fragments changes from 0 to 2, just reflecting the fact that both of these threads have individually contributed 2 to the overall sum of x. So when the parallel composition is done in the main thread, we again obtain the separating conjunction of the post conditions of both of these threads. So we again own gamma 1 fragments and gamma 2 fragment. We know both of them are 2. And so together with the invariant, we will be able to deduce that x must be the sum of these two. So it must be 4. Now let's look into how exactly the proof works for both of these fetch and add threads. In the left thread, the first thing that we do is the same as in the previous proof which Joe presented. We open the invariant, and so we obtain ownership of both x and the authoritative parts of both of these ghost variables. And now we can exploit the fact that we own the authoritative and the fragment of gamma 1. We own both sides. So by the entanglement property, we can say that n1 must be 0, because we know the definite value of the fragment. We can deduce the definite value of the authoritative. So we can replace n1 by 0. Next, the code is executing a fetch and add. So we have ownership of the variable x for this. We are allowed to do the fetch and add. And the effect of the fetch and add is to change the current value of x from n2 to adding to 2 plus n2. So we're adding 2. Now we are almost done. We would like to close the invariant again, but we cannot yet, because we have updated the physical state of x, but we've not yet updated the ghost state gamma 1 to reflect the fact that the left thread has now contributed 2 to the overall sum that's stored in x. So now we are using this rule, which, given that we own both parts of gamma 1, lets us update gamma 1 to a different value. We're using this rule to update the value from 0 to 2. Now we are in a situation where we can close the invariant because our ownership of x, as well as the authoritative parts of gamma 1 and gamma 2, exactly lines up. X is the sum of the two ghost variables, so we can close the invariant and complete the proof. And the exact same thing will happen in the thread on the right, except, of course, that gamma 1 is replaced by gamma 2 everywhere, and the rows of n1 and n2 are swapped. What remains to be done is verify the read of x at the end of this program and show that we indeed get 4. So again, we open the invariant. And this time, we now own the authoritative and the fragment of both ghost variables. So we can, by using the entanglement property twice, deduce that n1 equals 2 and n2 equals 2, which of course means that x can only be 4. So we can perform the read using this property, and we can deduce that 4 must be read, and then we have to reestablish the invariant, but that's easy because nothing changed. So this completes the proof that the program indeed will return exactly 4. So now is the time to take back a step, because we've seen 2 examples of how to do reasoning in Iris, and we've seen 2 kinds of powerful reasoning principles at play. On the one hand, we've seen invariants, which let us share state across multiple threads, and we've seen ghost variables, which let us combat the information loss that is otherwise inherent when using invariants. However, those are not the only kinds of reasoning principles or mechanisms that one might want to use when reasoning about a concurrent program. So for example, you might have heard of the idea of fractional permissions, which lets you take apart this points to fact. So instead of one thread exclusively owning a location, many threads can own it a bit, and they can all read from it concurrently and in an unsynchronized fashion. So this is great for representing read-only concurrency. Or you might have heard of the idea of a state transition system or monotonic state, which plays an important role in verifying fine-grained concurrent data structures. So how can we be sure when we are committing to using any kind of verification tool or program logic that we will have available all the mechanisms that we will need? Well, the answer in Iris is that actually Iris itself doesn't provide any of these mechanisms. Instead, it provides a more low-level fundamental building block, which is flexible enough to encode all of the things listed on the slide and much more. So the rest of my part of this talk, I'm going to explain what that building block is, and it's called ghost resource ownership. First, we start a little abstractly here because we have to capture what the idea of a resource is. In Iris, resources are described by resource algebras. If you've heard of partial commutative monoids or PCMs in the context of separation logic, this is very similar. The basic idea here is that we can think of a resource as something that a thread owns. And so one key operation that resources must support is if there's multiple threads, we must have a way to compose what they own. So we can say when the threads are done and the parent thread inherits all resources, what do they own? So there's a composition operation which takes in two resources and returns their composition. And the composition operation is associative and commutative because it really shouldn't matter in which order we are putting the resources of the threads together. And in fact, parallel composition itself is associative and commutative, so it would be strange if something wouldn't work out if composition wouldn't have that property. And the other ingredient here, and that is the non-standard part deviating from partial commutative monoids, is this idea of a validity predicate. So the central the problem this is solving is that some combinations of resources make no sense, right? So we've seen this entanglement property for the ghost variables. If one thread would claim the ghost variable as value 5 and the other says it's 10, that's just a nonsensical situation that should never be allowed to occur. So we need to have some way to say that certain resources or certain combinations of resources are invalid. And that's what the validity predicate does. It characterizes the subset of resources which are actually valid. And there is a technical axiom we need for this, which says that if the composition of two resources is valid, then both of its pieces are. Now, this is just completely abstract and algebraically. This has nothing to do with logic yet. The connection with logic comes up when we are putting resource algebras into Iris. So as a user of Iris, you get to define any resource algebra you want, and you may use it for doing your reasoning. And the way this works is that Iris provides this assertion written with a dashed box. And inside the dashed box, you state the resource that you own. So you state some element of a resource algebra which claims that you own that corresponding ghost resource. And since ghost resources, typically you need many of those, they also have a name. So there's many instances of the ghost resource that you might have floating around, and gamma identifies which instance of the resource you're talking about. So now let's see with a concrete example how resource algebras can be used to encode the ghost variables that we use to verify that our example program returns 4. First of all, we have to define what are the resources of our resource algebra. In this case, we first of all have resources representing authoritative and fragment ownership of the resource of the ghost variable. And because we have to define composition, we also need to add another funny looking element with this double circle, the authoritative fragment part, which represents ownership of both the authoritative and the fragment. And finally, we have a bottom element, which is the invalid element. And we use this to represent combinations of resources that don't make any sense. Correspondingly, the validity subset is defined to be everything except for bottom. The key of every resource algebra definition is its composition operation. But with ghost variables, there's not a lot going on here because there's not many compositions that are even possible. The only thing you can do is if you own both the authoritative and the fragment, then you may compose them to own the authoritative fragment resource. And the key property of this composition rule here is the side condition, which says that n and n prime must be equal. This reflects this entanglement property. It means that if you're composing authoritative and fragment parts where they are unequal, then we get the bottom result, so we get an invalid resource. Based on this, we can now define these assertions that we've seen in the logic. So this is a common pattern in Iris. You need some assertion, you need some reasoning principles, and you define it in terms of lower level resources that you can and then you build up your new abstraction And once you've done the definition once and proved the lemmas, you never think about the definition again. In this case, what we're defining is we're saying the hooked arrow authoritative part for ghost variable gamma with current value n is just ownership of the instance named gamma of this resource algebra where the element that we own is authoritative n, and the corresponding thing is we do the corresponding thing with the fragment as well, where we own the fragment element. So this is what we need to define our ghost variables, but of course that's only half. That now we're at best halfway done, because we also need to actually prove the reasoning principles that we need for ghost variables. And those can, in fact, be all derived from a few general reasoning principles, which Iris provides for any resource algebra, and which are good enough to derive whatever, to prove whatever you need about your own resource algebra abstraction. So first of all, let's look at these axioms. So the first one that we see on the slide here is the allocation rule. So it says if you have a valid element of some resource algebra, you may allocate a new instance. A fresh name gamma will be picked, and then you will obtain ownership of that resource algebra element. The second rule says that owning the composition of two resource algebra elements is equivalent to separately owning the elements A and B. And this is extremely powerful because, since remember that composition is user defined, you are controlling what composition does. So by extension and by this law here, this means you are controlling how separate and conjunction behaves on these resources. And this is what gives resource algebras their flexibility and their power. And finally, the last rule reflects the principle that only valid resources can actually exist in the logic. So whenever you own any resource A, you can deduce that it must be valid. Now let's see how we can use these laws to derive the proof rules that we need for ghost variables. The first rule we're going to look at is allocation. So unsurprisingly, we're going to use the allocation rule to first deduce that from true, we can obtain ownership of the authoritative fragment resource with some value n. This one, the resource is always valid, so the validity condition is satisfied. And then for the second step, we're going to use the composition rule, the second rule at the top, to take apart the authoritative fragment n in the authoritative n and the fragment n. And this is well defined just by the fact of how we chose to define composition. Next, let's look at the entanglement law. So we have ownership. We assume ownership of two parts of the same ghost resource instance, where we have authoritative n and fragment m. We want to deduce n equals m. So for this, we will first merge these two separately owned ghost resources to owning the composition of authoritative n and fragment m with the composition law. And then we can deduce that that composition is valid using the validity law. And if we now look at the bottom of the slide at the definition of composition and validity, we can prove that the only way that the composition of authoritative m and fragment m is valid is if n equals m, because in any other case, the composition is bottom and bottom is not valid. This covers the first two proof rules, but now there's still one more missing, which is the proof rule for actually updating the ghost variable to a different state. And in fact, that's the most interesting thing you can do with ghost resources. So here's the general principle for that. The idea is that if you own some ghost resource A, you may update this ownership to some different ghost resource B if you can do what we call a frame-preserving update, written A squiggly arrow B. And to understand the definition of this squiggly arrow, it's useful to take a global view of this. So imagine that there are all these threads that own some part of this ghost resource. So thread 1 owns A, and thread 2 owns another part, A2, and so on. It will always be the case, this is a key invariant that Iris maintains, that the composition of all of these resources is valid. And the idea of the frame-preserving update now is that thread 1 may do anything it wants to its resource as long as it doesn't step on any other thread's toes. So it must maintain this global invariant that the global composition is valid. So formally speaking, this means that we have to show for every frame for every frame AF that is valid when composed with our resource A. So we can think of this AF as being the composition of what everybody else owns. AF is equal to A2 composed and so on composed AN. For every AF that is valid when composed with A, we have to show that it's still valid when composed with B. And this reflects the idea that we have total freedom to do whatever we want with our resource, but our freedom ends where the other thread's ownership begins. We can't destroy what they own. So now let's see this rather abstract idea in action by looking at the update rule for ghost variable. So here I'm showing it again. We are owning both of these hooked arrows, which remember just unfold to owning the authoritative n or fragment n element of ghost instance gamma. I want to change it to a different n prime. And so by the proof rule for frame preserving for ghost resource updates, this amounts to showing a frame preserving update from the authoritative fragment ownership of n, squiggly arrow, authoritative fragment ownership of n prime. So let's unfold the squiggly arrow. What this means is that we assume that we are given some frame which is compatible with authoritative fragment n, and we have to show it's still compatible with a new element. But we can already stop here because there simply is no element that's compatible with authoritative fragment n. By the definition of composition, every possible frame will yield bottom when it is composed with authoritative fragment n. So the left-hand side of the implication is false, and so the overall frame preserving update holds vacuously. This was just one example of using resource algebras in Iris to obtain interesting ghost reasoning principles. And most of the time we are doing a proof, one key step in this proof is to pick the right resource algebra that we will need for the job. However, you don't have to define new resource algebras all the time. In fact, you barely ever have to do that because Iris comes with a large library of already existing resource algebras that are fairly general and that can also be composed in many ways. So for example, Iris comes with the authoritative resource algebra, which generalizes this idea of the authoritative and fragment bits that we've seen with ghost variables. And it also comes with an exclusive resource algebra reflecting the idea of one thread exclusively owning the entire state and no other thread owning anything. And we can compose auth and excl to obtain exactly the resource algebra that we used for our proof with this ghost variables over natural numbers. However, Iris also comes with some other resource algebras that are often used. For example, there's a fairly simple resource algebra for fractions where composition is just addition, but only elements less or equal 1 are valid. So we can make sure that we never own more than one of the entire state of the fraction. And we can also define a resource algebra on natural numbers where composition is addition. We can compose this fraction and the addition resource algebra together with auth to obtain a more powerful version of ghost variables, where we in fact only need one ghost variable to prove our example that the fetch and add returns 4. And we don't, in particular, this means that no matter how many threads there are which do a fetch and add in parallel, we can do the same proof. We don't need to add a new variable for each thread. We haven't discussed this example in the talk, but you can find it in the Cog material for this tutorial. And there are various other resource algebras I'm not mentioning here, and also various combinators, so that resource algebras can be lifted through products, sums, finite partial functions, and so on. So overall, this provides a large library of versatile resource algebras, and most likely, whatever you need for your verification job is already going to be available in this library. And if it isn't, you still have the opportunity of defining your own resource algebra for your task. So this brings me to the end of my part of the talk. I'm now going to hand over to Tej for the interactive demo.
All right, so I think what I'll do actually at this point is take some time for questions. We can answer questions for a little bit before I move on to the interactive part.
That also works for me.
Could I just ask Ralph to go back a couple of slides to the example of one forwards? That one, thank you. Sorry, I was trying to take notes and I wasn't quite quick enough on this slide. Thank you.
Oh, there's no question. Just OK. Yeah, you can find the slide PDF in the tutorial material repository as well.
I wasn't quite sure why the n.af is always bottom. That was the bit I was still trying to figure out in my head when you changed slides.
Right. So basically, if you go back to the full definition, if you look at the rules for composition, there's no rule here which says that you can compose auth fragment with anything to get anything but bottom. So we'll always be in the other combinations equals bottom.
OK, got you. Thank you.
So I mean, this is not very sophisticated. Most of the time, frame preserving updates are more interesting than this. This is a particularly degenerate example because our resource algebra really only consists of these two elements and their composition, and there's not much going on.
Thank
you.
You
If anybody else has questions, feel free to just unmute yourself and talk.
You mentioned that the logic is parameterized with respect to the programming language. Is that something you're going to talk about later, or is now a good time to discuss how that works?
We won't go into that more, so now is probably a good time to talk about that. So to some extent, this was a bit of a white lie in that Iris is actually structured into several layers. And there's a layer which is completely language independent. And then there's a program logic, which is parameterized by the language. And then that language is instantiated with a particular example language. So really, it's more appropriate to say there's an entire layer of Iris which doesn't know anything about programs. It's not really parameterized at all.
Do you have a good pointer to, like, let's say I wanted to plug in a different language and wanted to get started with that. What's a good, what would be a good place to start?
As far as I know, what everybody has done is basically copy pasted the heap length example and then made modifications to it. This will make sense the closer your language is to heap length, which is basically a lambda calculus with fork and readable references. I think you're welcome to ask on the channel if you have a more detailed question, especially if your language does not look like a lambda calculus. Then things will be harder.
Yeah, the language interface is not, there's no outside of Coq documentation of the language interface currently. Yes, that's why the copy paste strategy is the usual one. But we have a chat room which you can find the link for that in the tutorial material and also on our Iris project website. And so if you need any support with that, we are very happy to help.
I think also the Iris from the ground up JFP paper kind of at least gives you some idea of the ingredients that go into this interface. And so that might make it easier to understand what's going on in the heap.
I mean, it makes heap lang more precise. It doesn't really say where the abstraction is. And in fact, there's multiple language abstractions where there's a most general interface, and then we have some helper layers to make it easier to instantiate the interface. So if your language is not at all like heap lang, it might be worth asking at the channel just to figure out if somebody has already instantiated Iris with a language like that, so that you can copy as many things as possible.
Thank you.
Just one question about the resource algebras. So the earlier presentation as PCMs, well, there were neutral elements, okay, because these were monoids, and here you're making do without neutral elements. Or is that something notable, or just because?
Yes, very, very good point. Our resource algebras do not have a unit, and that's in fact a very important feature. So if you consider at least one of the examples that if you consider already this resource algebra that we used for the example here, then it doesn't have a unit. Our ghost variable resource algebra. Or if you consider the resource algebra of fractions, which exclude explicitly, that's very important for them to work, exclude 0, it doesn't have a unit either. So the fact that resource algebras don't have a unit is one of the key enablers for being able to define resource algebras, larger resource algebras by composition of smaller resource algebras. This is a bit hard to say in the abstract. But to give one concrete example, what we can do this way is we can, if we consider the product of fraction and any other resource algebra, doesn't matter what it says here, then because fraction doesn't have a unit, this means that if you own 1 comma anything, you know that there cannot be any frame. You know that there can't be anyone else owning any part of this. So even if this resource algebra here is extremely happy to share, and there's no way to make any exclusive statements, like with nat+, every element is valid if you just have natural numbers in addition, you can still obtain meaningful frame preserving updates by pairing it up with a fraction, which kind of kills away all the units. So this composition wouldn't be possible if our resource algebras had units.
Okay, that makes sense. Thank you.
If you want to know more details about that, the Iris from the ground up journal paper discusses this at great length. And of course, we are also always happy to answer questions in the chat also later here in this call as well.
One more question about the slides. For the exclusive algebra, do you mean that composition are always not defined when we are composing elements from X, or those are not in X?
Basically, yes. I mean, so strictly speaking, our composition operation is total, so we cannot make it not defined. So, but instead what we do is that exclusive X, the carrier, the elements, the resources of exclusive X are all the elements of X plus a dedicated invalid element, and every composition yields that invalid element. So that in that sense, it's like the bottom, except that everything is just bottom. which means every frame preserving update is valid because there's no possible frame. And this sounds degenerate, and it is, but it's still useful when you compose it with other visual algebra combinators. So for example, you can consider finite partial functions, where composing two finite partial functions is you just compose pointwise. If you now take finite partial functions with and you make the codomain, you make the element type exclusive of something, then you exactly recover the usual heap PCM, where composition is only defined if the domains of the two heaps are disjoint. So this is just one of the ways in which the Iris approach can take well-known PCMs and decompose them into smaller and individually reusable pieces.
And is that invalid element in X or not in X?
Excuse me, you're very quiet. What was the question?
Oh, sorry. So you said that like when it is undefined, the result is just the invalid element, like bottom, and that is not in X, right?
Yes.
Yeah, that's
you're adding an artificial extra element.
Okay. Okay.
So it'll be a value in xcal x, specifically in the carrier of xcal x, but it's not an element of X.
Mm-hmm. Thanks.
Those are very good questions. Thanks a lot.
Okay, I think I'll start sharing at least. All right, so what I'm going to do from here is I'm going to switch over to the Coq implementation of Iris. And one of the key ingredients to me that makes the Iris implementation the Coq implementation so useful is the Iris proof mode. So we have a mechanized soundness proof of Iris, but how do you actually reason on top of the logic? And this is especially important in Iris because, as we said, it's factored into smaller pieces. So we want to do as much of reasoning as possible on top of the logic rather than, say, in the model. So the goal of the Iris proof mode is to be able to reason in Iris as a logic in the same style as reasoning in Coq in the calculus of CIC. What that means is that we want to have a context. So Coq gives you a context of hypotheses. Similarly, in the Iris proof mode, we'll have spatial contexts with spatial hypotheses. So you're generally going to be proving an implication in separation logic, and you're going to have some hypotheses that are in the separation logic, like ownership or points to facts or ghost variables, that kind of thing. Next, Coq has tactics for manipulating the context, introducing and eliminating connectives, things like intros and split and destruct. So the IPM has tactics for introducing and eliminating the separation logic or Iris connectives, including destructing hypotheses, introducing the existentials, again, all this similar sort of things as Coq. And finally, the IPM is just implemented as a Coq library. It's essentially a collection of notations and tactics, largely powered by type classes. There's no OCaml plugin, there's no extension to Coq directly. It's really implemented at a user level. Okay, so that's enough talk about the IPM. Let's see the IPM. The way that I'm going to demonstrate it is by showing a formal proof of that swap example that Joe alluded to. And this is going to be a proof. So I actually have to implement swap in some concrete language. So I'm going to implement it in heaplang, which is sort of this example OCaml-like programming language that ships with Iris. Okay, so these strings are the variables of heaplang. So this is a heaplang value. It takes two values x and y. This bang is a load. So it reads x, stores y into x, and then restores the temporary. So now we want to prove that this thing is correct according to a nice separation logic spec. Okay, before I go to this, so this is just a program. Now we're going to start a section that actually has the Iris proof. I'm going to skip over a few things here. This is a simplified version of exercise 01 swap, which has much more detailed comments and some exercises for you to fill in. So this is not as well commented because I'm going to be talking through it instead. Okay, before we get to the Hoare logic proof, first I'm going to show just a separation logic tautology to show how the IPM works. So here's a nice little separation logic tautology. It uses some exists, some stars, And this thing is a magic wand. So you can think of this as this whole lemma is an implication. It says it says these three things imply these things. We're basically moving this existential out and dropping R. Okay, so the first tactic that we're going to issue is intros and then this pattern. This is a little bit like if you were to do something like this, if this were Coq, but it's within the iris proof mode, and that's why it uses a string. I've written below a simpler version of this. So this is introducing a hypothesis and then immediately destructing it. Okay, so now let's see on the right side what that did. So this part is a normal Coq context. And then this is just a bar that was drawn by company Coq. And then below that, we have what is the Coq goal. The Coq goal contains the iris proof mode context. This is where the notations come in. So the iris proof mode itself has a spatial context, which currently has these three hypotheses we just created, and then a separation logic, a spatial goal, which is exists A, phi A star P. And these hypotheses we can now manipulate in the same way that we manipulate Coq variables using these tactics. So for example, I'm going to destruct that existential H phi, and I'm going to name the variable X. So this produces a Coq variable X. And you can see that H phi is no longer an existential. So we've eliminated that existential in the hypotheses. Just to take a step back, remember that what we're proving is a separation logic implication this whole time. We're proving that these three things starred together imply this goal, but we get to think about it as if they were just normal hypotheses, right? We don't normally think in Coq that we're proving the conjunction of all of these things implies the goal. We just think of them as being just separate hypotheses. So this really raises the level of abstraction of this reasoning. Admittedly, this is not a very interesting theorem. It's just a tautology. You could probably prove this with automation. But program proofs, especially with Go state and with concurrency, tend to have lots of interesting steps in between that we can't automate. So just to wrap up this proof, I'm going to finish up this proof. There's one interesting thing that we need to do, which is we need to prove a conjunction. And normally in Coq, this is not a big deal. It's very easy to prove conjunctions. But in separation logic, conjunctions are actually a little tricky because we have to decide how to split up the hypotheses. So we're not allowed to use, because this is a substructural logic, we're not allowed to use these hypotheses on both sides. And so the IPM split tactic takes a pattern, essentially a list of names, that tells it which side you want to use which hypotheses on. So in this case, I'm choosing to use H phi to prove the left-hand side and the remaining hypotheses to prove the right-hand side. And then with that correct split, both subproofs are easy. You can just be proved by assumption. Okay, so the next thing that we're going to do is we're going to see this proof of swap. The specification looks about as we wrote it in the lecture. One second, let me just reformat this thing nicely. So it's a Hoare triple. We have 2 points to facts, x points to v1 and y points to v2. And we're just going to swap the values of these two things. Now, the first thing that we get exposed to is that this notation in Iris, so now we're in the program logic part of Iris because we're proving a Hoare triple. We don't actually use Hoare triples directly in Iris to encode program correctness. We use Weekes preconditions, which are more convenient for a number of reasons, which I don't have time to get into here. And so there's no good way for me to show you what this desugars to directly. But after we introduce the hypotheses, you can see, I can show you what we just did. So whenever we write this PEQ as a Hoare triple, it's a notation which desugars to this expression. And you can think of this expression as being a continuation passing style version of the Hoare triple, where there's 2 things going on here. So first, we're using Weekes preconditions. So if we were just using Weekes preconditions, then we would desugar this to something that looks more like this. So that Hoare triple is equivalent to this this implication involving a Weekes precondition. And then in addition to that, we've also built in sort of an application of the frame rule. Sorry, this is like an application of the rule of consequence, where we're going to prove this for an arbitrary postcondition and an assumption that the desired postcondition Q implies this postcondition. And it's logically equivalent to just doing this Hoare triple, but it's a little bit more convenient to apply because it uses an arbitrary postcondition. This lemma will apply even if you apply it in a context where the postcondition isn't literally x is v2, star y is v1. So that was a long explanation, but really the upshot is that basically this is just the precondition, and you have to carry around this extra fact, which lets you prove the postcondition phi. And we'll apply that, we'll hang on to that hypothesis and apply it at the very end of this proof. Okay, so most of this proof is just going to be symbolic execution. So this swap is a few beta reductions. So we can use these automation tactics to reason about the beta reductions. So WP lam does a reduction, WP let reduces this let. You can see that as we work interactively, we're always proving a WP, but of a progressively simpler program. We're kind of going through the program step by step. Loads are pretty easy to automate the proof for. So WP load just automates applying the weakest precondition rule, the Hoare triple for loads. Because this program is so simple, we can do it using almost entirely automation tactics until we get to the postcondition. For technical reasons, we need to execute this imod intro. This is related to ghost variables. So at this point, we would be allowed to make some more ghost updates before we prove the postcondition. But we don't need that for this proof, so I'm just going to execute imod intro to get rid of it. Then as I said, so this proof is quantified over an arbitrary postcondition phi. And to prove that, we're going to apply this post hypothesis. So here you can see that we're applying a spatial hypothesis, which is an implication. That works just like applying a Koch hypothesis, which is an implication. And then we finish off the proof by splitting and applying the hypotheses. You'll see in the exercises that there are simpler ways to do this proof. We can do all of this stuff a little bit more conveniently than I did here. But I just wanted to show this using very simple tactics first. Okay, are there any questions at this point? Because this is a lot of IPM stuff, and after this I'll go into if we have time, I'll talk about a slightly more sophisticated example.
So there's a question in the Clouder chat here, just more of a logistical thing, I think. But someone was wondering if Iris works with Koch 8. I think it's 8.12.
Yeah, so the question was specifically about 8.12.0. I don't believe there were that many serious changes between 8.12.0 and 8.12.2. Ralph, do you remember if something broke?
Yeah, I think I already answered in Clouder, but maybe Clouder didn't show that. I think it should work. So generally, we are testing Iris on the latest patch releases of at least the last two, usually the last 3 or 4 major Koch releases, or minor, I guess is what you would call it. So 8.11 to 8.12 to 8.13.0 are currently supported. And so we're not actively testing 8.12.0, but I think it should work.
Yeah. I believe if anything broke, it was that the output changed, and so the tests no longer pass. But I believe Iris does still work. Okay, so if there are no questions, I think. Oh, go ahead.
Sorry, there was also one question in the Zoom chat about why they are called Texan triples. The answer is slightly embarrassing because it was a joke that stuck. I mean, as you can see, the notation has 3 curly braces, which is a lot of curly braces. So it's very big Hoare triples, and everything is bigger in Texas. So clearly they are Texan triples. There's no deep reason. They just had to have a name, and that's the name that they have, and now it's stuck.
Okay, so what I'm going to do is I don't have time to walk through both of these examples, but I have 2 proofs here. So these formalize the 2 proofs that we saw informally in slideware in Koch. So here I'm just going to go through this proof that this program returns an even result. So this only requires invariants, and we don't have to use GoState. Okay, so first we need to define the invariant involved. Actually, I think I can maybe switch to, sorry, I don't remember which slide. Ah, nice. Okay, so we're going to allocate this invariant, exists n, x points to n, even n. And that actually looks almost the same in Coq. One slight technicality, the proof requires reasoning about this FAAR2 expression twice. So I factored that out into a lemma. What I'm going to do to present this is I'm going to skip over the lemma, and then I'll come back to it when we actually need it. So the first thing that we do is we do some symbolic execution, we get through the allocation, and then we need to allocate this invariant. So before we can, so as Joe pointed out, we have this points to fact. We can't pass it to both of these sub-expressions. We have to first wrap it in some sort of invariant to share it. So the way we do that is we allocate the invariant parallel add in, which you can see on the right-hand side. The way that we do that is, so the IPM has very general support for modalities, and the way that ghost updates are implemented is using a modality, and invariants are themselves implemented as ghost updates. So there's actually basically one primitive tool that you have access to, which is the ability to execute a ghost update. So if we look at the invalid rule, this view shift thing is just the same thing as executing a modality. If this doesn't make sense to you, the Iris from the ground up paper does a much better job of explaining what is really going on under the hood with invariants. But when you're in the IPM, the upshot is that you execute imod in order to get the right-hand side of an invariant. In order to allocate an invariant, we do have to give up the resources that initially satisfy the invariant. And so I'm going to prove this using our points to 0. I'm going to skip over the proof. It's not that interesting. We basically, except that maybe there's one interesting thing to see here, which is this iframe tactic. So it's pretty common to run into a situation where you have a bunch of hypotheses that you need to match up with things in your goal. Before, I did a proof like this using iSplit and then iAssumption manually. This is really, really common in separation logic. So there's a tactic in the IPM called iframe, which is devoted to this kind of matching process of dismissing obligations using your hypotheses. An iframe can actually also prove the z even of 0, I think, because z even of 0 is actually just true if you simplify it away. Okay, so now that we have an invariant, we can apply the parallel composition rule in order to reason about both sides. There's one interesting thing that's going to happen here, which is that, so the way that Joe explained it is that there's an invariant assertion, this inv and parallel add invar. This is like the boxed invariant assertion that we have on this slide. There's two things that are different about it. One is that it uses the keyword inv instead of being the box, because this is ASCII. The second difference is that it has a name n. Again, this is for reentrancy. So we shouldn't be allowed to open the same invariant twice. And so Iris tracks this. It's generally not going to matter because you're not going to try to open the same invariant twice. But it shows up in generic proofs and it's needed for soundness. Okay, so now in Joe's explanation, what we needed to do to carry out this proof is we needed to duplicate that invariant assertion in order to have two copies that we can send to both sides. The IPM has a much nicer way to do this, which is that a subclass of propositions is so-called persistent. All persistent hypotheses are also duplicable, but persistent is a slightly stronger condition. Invariants are not just duplicable, but they're also persistent. And what the IPM is able to do is it actually puts all the persistent hypotheses in a separate context. So you can see that this IPM goal is being displayed with, the way to think about it is that there are two contexts. There's a list of hypotheses here that's separated by this arrow in a box. And then there's another list here, which is all the spatial things. Because the persistent resources are all duplicable, when we split the goal, for example, when we apply the parallel composition rule, we actually get to keep all the persistent hypotheses in all three subgoals. It's not necessary to decide where they go. And furthermore, it's not even necessary to duplicate them. I see a question in chat that would it be possible to move persistent hypotheses to the Coq context part? Okay, that's a very good question. So the answer is no. The reason is that the persistent hypotheses are, okay, so the Coq hypotheses are sort of pure things. We have all of these at the Galena level. These persistent things are a property of the Go state. So they're still within the Iris logic. The invariant assertion says something about the Go state. The Go state has some piece in it that tracks all the allocated invariants. And this inv thing says that indeed there's an invariant that has this contents. So it can't be lifted to the pure level because it's not a global property. It's like a property of the current state of separation of the separation logic assertion. Okay, so that gives us the duplication. So that kind of takes us to this point in the proof where we've split up the invariant assertion. Also, because these things are persistent and they're freely duplicable, we don't need to carry them around in postconditions. Even though the example does this, the lecture slides do this for clarity, just to make these rules look a little nicer. So the next thing we need to do is actually reason about the body of fetch and add that requires opening the invariant. So I did that in a separate proof as a lemma. I have to, again, introduce the invariant, and then now I do the most interesting step in this proof, which is to open the invariant. This implies that invariant, so we could manually open the invariant by applying some appropriate lemma, the way that the slides do. But this is a very common thing, and there's some nice, so the IPM has some nice support for it within a dedicated tactic, inv. So I guess let me do this in a slightly slower way. So let me just open the invariant. There's a bunch of stuff that just happened. First, this is the contents of the invariant, guarded by a later for technical reasons. And then you can see that the goal became considerably more complicated. So there's two things that happened. First, this at top minus n is tracking that we're no longer allowed to open this invariant again. So that prevents reentrancy. And then this goal says, even after we're done reasoning about this expression, we're still allowed to execute ghost updates. That's what this whole modality means. You can ignore that for now. We're not going to need to use that. But more importantly, we still need to prove parallel add inv r in the post condition. So this is what, when you open an invariant, it creates an obligation that you need to also satisfy the invariant afterward. One thing that didn't come up here is you can only open invariants around atomic steps. So I'm going to demo what happens if I try to do something on a non-atomic step. So here is a version of that code which has this approximately the same behavior as fetch and add, but it's non-atomic. And so it doesn't actually preserve this. It might not preserve this invariant because
your parentheses are the wrong way to make it actually fetch and add. Now you're adding two to the address, yes.
Okay, cool, thanks. Right, so now my goal is, I can't actually open an invariant around this assertion because I'm not going to be able to prove that this expression is atomic. That is, it does not reduce to a value in a single step. It takes about 2 steps. So we really need this to be a fetch and add. Otherwise, this proof is not going to. This proof strategy is not going to work.
And of course, that just reflects reality, right? Like this program wouldn't actually have the same behavior if this wouldn't be an atomic fetch and add, because there could be interleaving of the 2 additions and the result would be different.
Yes, yes. Yeah, so I think this particular proof would still go through because we still prove evenness. But
oh, that's fair.
Yeah, but the program is weird and needs different reasoning.
And the one which proves that it returns 4 certainly wouldn't be true.
That one would not work. That one would not be true. Okay, so after we open the invariant, I think the Coq is confused. 1 sec. Okay, after we open the invariant, we can reason about the fetch and add, and then we can wrap up this proof by just reproving the invariant. I'm going to skip over these steps that just kind of manipulate hypotheses. I think the most interesting thing is that we need to actually prove that n+2 is still even, which is basically just this lemma from the standard library that says we can add even numbers. Okay, I think I'm going to stop here. There's one more step to the proof where we actually prove that after the two threads return, we return an even number, but it's not that different. We basically open the invariant and learn that the result is even. Okay, so I think we'll just hang around and take questions. This is a good time to go and download the repo. Sorry, one sec. For the exercises, you're welcome to get started on the exercises. We can help you now as well as through POPL. And if you really want to deep dive into Iris, there's two sort of non-Calc resources. Iris from the ground up is a very detailed explanation of the logical foundations. And the Iris lecture notes are a semester-long course that goes over, again, the basics of Iris without the Calc implementation. And we're also happy to help in person if you have specific questions.
And for everything related to Iris, the website for Iris itself is iris-project.org. So you will find all these links there, as well as all the other links you might look for.